Just bad kids, friends. You're bad.
Are you telling me how to like do the visa? Well, at least you got
I don't know why 24 is
they ask you why did you
Okay, good morning everyone. Good morning. We're going to be looking at a problem on radial conduction, and we will set up the thermal resistivity to conduction for radial systems, for cylindrical systems. Okay, and my plan is to do this using a problem as an example. So problem. So we have a hollow cylinder. Okay, so this is a hollow cylindrical tube. I'm not drawing the length of it. It's a hollow tube. The subscript for quantities that are involved with this tube will be little t. Okay, so this is little t. There is a very hot fluid that is passing through this tube. So if you draw the length and so on, through here, there is very hot fluid passing through. So that comes in at T infinity I and Hi. Okay, so T infinity I is 120 degrees Celsius, and then Hi is the convection heat transfer coefficient. It is 100,000 watts per meter square Kelvin. Okay, so which implies the higher the value of H, the faster the convection heat transfer rate and the speed of the flow and all these things. Okay, which we will see as we come to convection later on. Now obviously, because of the fact that there is a hot fluid flowing through this pipe, and then the pipe is made of maybe metal, there is going to be a certain amount of heat loss taking place. To prevent that heat loss, we will put a layer of insulation. Okay, so there is another layer here. Okay, so this is an insulation ring here. And the subscripts that are associated with this will be capital I. And I'm going to write down the radii and all that. And outside, this is surrounded by ambient fluid. So outside is T infinity naught, and then H naught, where T infinity naught is 20 degrees Celsius. H naught is 10 watts per meter square Kelvin. So there is not much of forced convection going on outside. It's more or less air which is moving at a very slow rate outside. And the following are the radii, and I'm going to draw them as individual rings here. So inner ring, and then the insulation ring. So there are three radii given to us. One, Ri, R naught, and then R capital I. Okay, so you see the insulation ring, you see the annular cylindrical shell, and then the annular shell is obviously hollow, so there is fluid flowing through here. and then there is fluid surrounding the outer layer. Okay? So the details are R naught is 1.67 centimeters. Ri is 1.33 centimeters, and I'm given a range of radii for the insulation ring. So Ri starts at 2, 3, 3.5, 5, 10 centimeters. Thermal conductivity, so this is material T, tube, insulator I, KT is some value, approximately 15 watts per meter Kelvin. And Ki is 0.4 watts per meter Kelvin. Okay, you're asked to ignore radiation, everything is at steady state, no energy generation within any of them. Steady state, 1D radial, Q dot is 0 in all portions. Ignore radiation because there is no emissivity given to you. No contact resistance, but I'll draw the circuit if there is a contact resistance so that it's useful for your homework. Okay? It's not a big deal that it is just adding one more resistance in there. What are the things we need to find? First thing is perform a surface energy balance on each of the rings. On each layer. Once we do that, obtain an expression for thermal conductivity of a annular cylindrical ring. Okay, so I'll obtain R conduction for an annular cylinder. And always remember, if you are talking about a thermal conductivity, it has to happen in the absence of heat generation. There can be portions of the problem where heat generation takes place. There are portions of the problem where heat generation may not take place. The idea of thermal resistance is valid in those portions where there is no heat generation. Okay, this is something we've discussed in the past as well. Alright, so those are two things that we need to do. Third thing, obtain the heat loss rate. Q dot for the range of the insulation radii for Ri, whatever that range is. Obtain it without an insulation ring as well. Obtain heat loss rate Q dot without insulation. Obviously this is a problem that will involve using MATLAB or Wolfram or one of those things, because you have to write a loop, right? You have to pick one radius for the insulation ring, perform the energy balance, obtain the heat loss rate. Pick the next radius, do the same thing. Okay? Then compare, which will obviously tell you some very odd things are going to happen. And so what our main aim, the centerpiece for the day, is we need to obtain the critical radius of insulation. Which I'm going to call as Ri subscript C, critical radius of insulation, and we will comment on this. And based upon this particular value, we will choose a certain radius of insulation for our problem. Okay, so choose a suitable Ri for our problem. Once again, this is an extremely standard problem in the realm of heat transfer. As a mechanical engineer, one should have encountered this problem at least once in their life before graduating, because this is of such extreme practical importance. Okay, and we will look at this problem step by step. So first part of the problem, when you're doing the energy balance, the surface energy balance, obviously the generation rate is zero, the problem is at steady state, and it is not necessary to draw each of these as big circles. I can just draw a small sector, draw the control surfaces, and perform the energy balance there. Okay, as I'm going to show you now. So over a sector, this is Ri, okay, the radius of the insulation starting from the center, defined that way. This is R naught, and this is R subscript I. Everybody able to see my figure clearly? Okay, so this is R little ri, this is R naught, the radius of the outer ring of the annular shell, and then this is the outermost radius of the insulation shell. Okay, so the insulation shell has a radius range from R naught to Ri. The annular ring, the pipe, has a radius range from Ri little I to R naught. Okay, so pipe is Ri, R naught, insulation is R naught, capital I. Outside is T infinity, inside is T infinity naught, and so on. So T infinity I. Okay, so that's a hollow piece. You're not seeing that here. And this is the pipe and layer of insulation. Now when I draw the control surfaces, I draw them across each of these small rings in the sector. So I'm going to draw my first control surface right here. Then my second control surface right at the edge of the outer ring R naught. Okay, and then my last one is going to be at the outermost radius of the insulation ring, and that's right there. Alright, so three control surfaces. 3, 2, and 1. No energy generation taking place within any of these, so we are good to go on that. Okay. Then all I have to do is draw the arrows. In many problems, most of the times, one can use intuition to figure out what the direction of heat flow is. Okay, in a problem like this, it is fairly straightforward to understand that there is no energy generation taking place in any of these rings. This fellow is hot, that person is cold, so the heat transfer rate is going to flow radially from the hollow piece all the way to the ambient. Okay. In certain other problems, it may not be possible, which means that you need to let the math do the talking. Okay, so you choose a direction for your heat transfer rate, and then you let the equations figure out, okay, is this right or not, based on the information given to you. Alright? So for this problem, it's straightforward. I'm going to have convection first. This is Q double prime convection I multiplied by the area. Okay, then this is going to go as conduction into the first ring here. So this is going to be Q double prime conduction I. Okay, multiplied by the area AI. It is obvious that if there is no energy generation taking place, the conductive flux will be a constant, right? So which means that I just draw this arrow here. This is Q double prime conduction I, or conduction O, okay, if you want, multiplied by the area A naught. Okay, this is for the material of thermal conductivity K suffix T. This goes into the insulation ring. So I'm going to have this guy here, Q double prime conduction insulation at that particular radius of R naught multiplied by the area A naught. I'm looking at the heat transfer rate, so flux multiplied by the area is the heat transfer rate. No energy generation within the insulation ring, so this arrow is just going to radially travel along with the same flux value, and so this is going to be Q double prime conduction insulation multiplied by A suffix I, which is the surface area at the radius R suffix I, and then obviously this is going to come out as Q double prime convection out times AI. And I'm going to write all of these things. Does my figure make sense to everybody? All of you are able to see my subscripts and so on? And I'll be rewriting them once again here, so if you can't see them clearly there, I have them here. Energy balance at each of these control surfaces, energy in is equal to energy out, no big surprise there. Okay, so energy balance, E dot in is E dot out at each control surface, surface balance. Okay, no generation, no storage, even if there is generation within the body. When you're doing a surface energy balance, you don't include those terms. Okay, so I have Q double prime convection multiplied by AI, which is equal to Q conduction I multiplied by AI. Once again, I'm looking at the heat transfer rate, which is the net rate of energy transfer into and out of the bodies or the control surfaces. Okay, this is equal to Q double prime conduction O A naught which is in turn equal to Q double prime conduction A capital I times AI, and which is in turn equal to Q convection outside. I'm skipping the intermediate steps in between. Alright, so convection between the hollow fluid in the hollow chamber and the first ring, then conduction through the first annular ring, then I'm going to have conduction through the insulation layer, and then convection out of the insulation onto the ambient. Very standard stuff. And since the rate of energy transfer is the same all through, I can make use of the idea of thermal resistance networks in those regions where there are no heat generation taking place. I'm going to draw this in the form of a thermal resistive network. We'll fill in some unknowns very soon. Okay. I start off at T infinity I, and then all the way from T infinity I to the first layer of the annular ring, I'm going to have convective heat transfer. So this is R convection I. I'm going to call the temperature at the inner ring as Ti. Then as I have heat transfer going from Ti to T naught, which is the temperature at the outer ring of the pipe, I'm going to have a conductive resistance, which we have to find out, or conduction through the material whose thermal conductivity is given to us as K suffix T. Then all the way from T naught to T capital I, which is the temperature at the outermost layer of the insulation ring, okay, I'm going to have an R conduction, capital I, and then T infinity naught, convection O. And just to be clear what temperatures I'm referring to, this is Ti, T infinity I, T naught, capital I, T infinity naught. Okay, so there is fluid inside here. So these are the different temperatures I am referring to. This is material of thermal conductivity K suffix T. This is Ki. Alright, we know conductive resistances, 1 by H times the area. Got to be careful with the areas here. I'm going to list the areas. They are not plane walls, so the area of cross section is not the same at each of the radii. Okay, so at some random radii, this is 2 pi r times L, where L is the length of the cylinder. So for each of these, I'm going to write AI 2 pi Ri times L, A naught 2 pi R naught times L, capital I, capital I times L. So far so good? Everybody clear on the figures that have been drawn, on these equalities that have been written out, a resistance network that has been drawn, and these are the temperatures I have specified. Okay? It is highly possible that we may not complete this problem today, so we'll come back on Monday and complete it. Okay. Before I go to the next step, which is to actually calculate the heat transfer rate, and I need to write down, this is Q. This is Q, and it is very obvious to recognize from the problem. Please note, I am given T infinity I, which is 120 degrees Celsius. I am given T infinity naught, which is 20 degrees Celsius. If I can somehow figure out these two conductive resistances, which are based on the property of the material, the thermal conductivity and the area and so on, the radii of the material and so on, then I can write Q. So from here, Q is T infinity naught minus T infinity I by R total, where R total is nothing but the net resistance of all these resistors in series, which is the algebraic sum. Convection I, conduction T, conduction I, convection O. Okay, so that's our total. And before I go in to find out this R conduction for cylindrical systems, one point I want to make. If we have a contact resistance, can you tell me where that contact resistance will make an appearance? If I had to have contact resistance, yes?
T naught.
It has to come in at the radius R naught, right? That is where the two dissimilar materials or two different bodies physically are contacting each other. It's not going to be in the hollow system here, because that is going to affect the convective heat transfer coefficient, which will be a function of the surface roughness and all these things, which we will calculate at some other point in time. Hopefully never. Likewise, T infinity naught as well. We will of course do it, don't worry. So if we have a contact resistance, it's going to come between the material of thermal conductivity Kt and Ki. You imagine contact resistance as an infinitesimally thin ring. Okay? So in some sense it will be something of that sort. Okay, and if I had to include contact resistance, here is how the network would look like. So if R double prime contact between Kt and Ki at the radius R0, how would the network look like? Similar to before. T infinity naught, T infinity I, then I have the rest of the temperatures Ti, then this is some T1 naught, T2 naught, T capital I, where T1 naught and T2 naught is the temperature difference between the innermost ring at the radius R0 and the insulation ring at the radius R0 due to the contact resistance. So in some sense, this would be T1 naught, that would be T2 naught. Okay? So there's going to be a temperature gradient because of the fact that these are dissimilar bodies contacting with each other, different surface roughness profiles. And if I write the resistances, R convection I, conduction T, conduction I, convection O in between. If you have contact resistance, what do you do to get the actual resistance? Yes? Divide by the area. So here I'm going to have area at that radius. So be careful here. So that's going to be by A naught. Okay? So this is if there was a contact resistance, which is not the case for us. So we will blithely ignore this case. But as you see, it's not a big deal to accommodate it. Alright, now I go to the second part of the problem. R conduction and likewise R conduction I is 1. Okay? We're going to do this derivation once and then we will use it for all our problems from now on. I start off with the inner shell. So between Ri, R0 with the following boundary conditions. T at Ri is Ti, T at R0 is T0. Let's say that these are given to me, these are things that I know. I start with the heat diffusion equation. I also know further that Q dot is 0 within this body, so and steady state as well. So my heat diffusion equation becomes very simply the following. KT by R, d by dr, R dt by dr is 0. Q dot is 0, dt by dt is also 0, so it reduces to this simple form. I can cancel off the Kt by R ratio on the left hand side, so this tells me d by dr, R dt by dr is 0. Integrate once, integrate twice. Okay, so if I integrate twice and once I get the following. So R dt by dr is C1, so that is C1 by R, P C1 ln R plus C2. C1. Should I get rid of it? Do I have any right to get rid of it?
It's not solid.
It's not a solid. I can get rid of C1 only if there is a solid body. And you see, if I have a solid body and if there is no heat generation, the temperature is going to be the same throughout, starting from the center all the way to the outer edge, because C1 is 0. So I will just have C2. But if I have a hollow body, a hollow cylindrical shell or a hollow spherical shell, I cannot get rid of this particular term, because my radius range is not starting from 0. It's starting from Ri to R0. So I will have a finite value for my temperature and also for logarithm R at the Ri and the R0 values. So please be careful. Okay, so I cannot get rid of the long R term. Okay. So I make use of the boundary conditions. So T at Ri is Ti, which is C1 logarithm of Ri plus C2. Likewise, the second boundary condition, which is C1 or not plus C2. Subtract one from the other. Log A minus log B is log A divided by B. Okay, so from here I'm going to have Ti minus T naught is C1 logarithm Ri minus C1 logarithm R0. Or if I rearrange it, look at this. C1 logarithm Ri by R0 is Ti minus T naught. But Ri is smaller than R0, so I'm going to flip the scales so that I write it in the following manner: or minus C1 is Ti minus T naught, or C1 is minus Ti minus T naught by logarithm Ri. Minus sign is important, and you'll see that in a minute. You can substitute and calculate C2. I'm not interested in doing it. I'm interested in finding thermal resistance to conduction in a cylindrical shell for one-dimensional steady state heat transfer in the absence of energy generation. Right? So I calculate Q at some radius R between Ri and R0. Okay? So this is going to be minus KT dt by dr, or minus KT d by dr of C1 logarithm R plus C2. I forgot the area, sorry about that. Multiply with the area. Multiply with the area. Don't forget, this is heat transfer rate, not flux. D by dr of logarithm of R is 1 by R, and so I have Q at R is minus KT. Area at any random radius R between Ri and R0 is the following: 2 pi R L C1 by R, where we have made use of the fact Make sense to everybody? Just rearranging things. Okay. Substitute for C1 and notice gone. Great news. So this is going to be minus KT or minus 2 pi L KT times C1, which is now going to be written as minus Ti minus T naught divided by logarithm of R0 by Ri. Negative sign cancels off. And so Q is Ti minus T naught. I'm going to bring the 2 pi L kT below the logarithmic term, just doing the rearrangement once again. Divided by that particular term. And compare this with or conduction. R naught is geometric, Ri is geometric, they are fixed values for a given problem. Length is fixed, most of the times you are not given the length, so just assume it to be 1. If you are not given anything, assume it to be 1 in the proper scale. KT is a material parameter, so this is a constant for a given material and for a given geometry, which is exactly how we would like conductive resistance to be. So by comparison, our conduction for any cylinder of length L and thermal conductivity K and the radius between Ri and R naught, our conduction is natural log R naught by Ri 2 pi Lk. When is this valid? Steady state. Q dot is 0. Alright, this is beautiful stuff. We're going to make use of it though. So we go back to our problem, where we have drawn the resistive network. Now we have a placeholder for this conduction resistance, so I'm going to write it for each of these things. So for us, our conduction T, which is for the pipe, okay, which are the substitute of T, this is going to be logarithm R naught by Ri. The larger radius by the smaller radius, always remember it that way. And this is 2 pi L kT for that radius range. And then I do the same thing for the insulation ring as well. So our conduction capital I, this is logarithm of R capital I by R naught, because Ri is greater than R naught, the capital I for the insulation ring, divided by 2 pi L Ki. Alright. I'm going to go back to my thermal resistance network. With your permission, I'm going to slide this. Yes, sir? Yeah?
Ri is greater than
Yes, Ri. R capital I is greater than R naught. You're right here. That is good. Thank you. Let's flip the inequality. Alright. I'm going to go to our problem here. Okay, so this is what we had. This is the equation that we have. I'm going to erase this side. So I'm now going to write the entire problem in terms of its variables. Okay. So Q, back to our problem, is T infinity naught minus T infinity I divided by 4 resistances. First one is the conductive resistance, so that's going to be 1 by Hi Ai. Okay, so that's the convective resistance here. Then the conductive resistance, which we have just written down there, two of them, throw those fellows into the mix. So plus logarithm R0 by Ri 2 pi L kT. Make sure that you're using the thermal conductivity of that particular body when you're writing the conduction resistance. Third one, Ri by R0 2 pi L Ki, and the convective resistance plus 1 by H0 A0. I'm going to unpack this further. Wherever I see an area, I'm going to write the actual area itself. So this is T infinity I. I'm sorry, this is I minus O. Hotter minus colder, right? That's typically the flow of heat. Sometimes my hands write faster than my mind. Yes, sir.
Why are we not using our contact?
Oh, because in this problem the contact is not given to us.
Okay.
If it were given, you can just include it as we specify. Divided by 1 by Hi Ai is 1 by 2 pi Ri L Hi. 2 pi Ri L is the area. Then write the next one. Logarithm of R0 by R little I. 2 pi L Kt. Third one, R capital I by R0. 2 pi L Ki. And the last one, plus 1 by 2 pi Ri L H0. Okay. Lot of writing. Now time for action. I'm going to substitute all these numbers. You're going to see it in my written solutions, but here I'm going to give you the results. So I'm going to make a table here. R capital I, heat loss rate Q dot. I start off with Ri as 0, okay? So which typically means that I cannot use this term here. So when Ri is 0, I do not have that ring at all. So Ri of 0, which means that you ignore this particular term. Does this make sense to everybody? There is no insulation ring, so why are you including its resistance? That's about it. Okay? Then I have 2 centimeters, then 3, 3.5, 5 and 10. And here are the values. This is what is called as a design problem, right? (106 watts) without any insulation. What do you think is going to happen if I add insulation? It's going to go down? Are you sure? One hopes that is the case, but it's impossible to prevent that. There is always going to be heat loss, no matter what you do. You cannot trap energy. Energy can only be transferred, the heat energy. Heat is not energy that can be stored. You can store thermal energy. Okay? So as you increase the radius of insulation, here is the funny thing. the heat loss actually starts increasing. Starts increasing, this is all in watts, goes to a value of 131 when I hit 3 centimeters of insulation thickness, radius, 133, then I come to 132 or 131.8, then when I come to a radius of 10 centimeters, 105. And so if I just plot this, this is Ri, this is Q. My plot is going to look something of the following sort. So what does this tell you? Is insulation a good thing or a bad thing? Depends on what? Depends on the radius that you choose. So if somebody says, hey, just put some insulation and forget about it, your question should be, okay, what the hell is supposed to be the radius? If it is something like this or something like that, I'm actually increasing the heat loss rate. You see, for heaven's sake, that's not the same thing as having an insulation, right? When people say insulation, you're reducing the heat loss rate. So, for cylindrical systems, for all these pipes that you're seeing here, there's a lot of design that goes into them to deposit chilled water or hot water and all these things to your homes and your dorms. There is a certain critical radius of insulation up till which adding the insulation is actually detrimental to the problem. And it's only after you go beyond that critical radius of insulation, the heat loss rate is going to start reducing. And depending on what your calculations were with the case of no insulation, you will have to go up to maybe 10 centimeters or more to actually start having any usefulness in putting in insulation on the system. If you decide to buy insulation for 2 centimeters and have it for a length of a pipe of 2 meters, you are wasting your money and your time. You might as well just not put insulation on it. And you had a question.
So with the lower value, so in this case, how the heat loss rate increases from about 0 to 3.5, would that work as more of a heat sink rather than an insulation at that level of thickness?
Heat sink. So the purpose of a heat sink is to remove heat.
Yeah, it's
Right,
to
right.
dissipate heat. So would
It is dissipating more heat in some sense. So if you're wanting to cool the fluid down within the hollow cylinder, then maybe adding insulation is actually not a bad idea.
Okay.
So it works in both ways depending on your purpose. Exactly. Absolutely. Absolutely. Yeah. Which means you have a question.
And this is independent of the T infinity out?
Oh, absolutely. Yeah. This is independent of the outside temperature. Yeah. Yes, sir.
If you keep increasing Ri, does your heat loss rate eventually approach a limit?
It will typically reach a limit. That is what we are going to be calculating actually, and you will see that okay, if my actual heat loss rate is 106 watts, and I want to just maintain it at that, I will go for a 10 centimeter insulation. It is also a function of how much money you are willing to invest and how much space is available. So those are your design considerations. Yes, sir.
Why does this behavior occur? I don't know if you can explain it at all or not. I'm just like.
Oh, we are going to explain that. We are going to explain that. So it is essentially a competition between the conductive resistance and the convective resistance.
Okay.
So importantly, it depends. In some sense, it is also dependent on the ambient temperature, as one of you asked. Is it dependent on the ambient temperature? It is dependent on the convection coefficient, then, which is a function of the ambient temperature to a small extent. It's a weak function of the ambient temperature, but it's a much stronger function of what's happening at the boundary between the insulation and the outside. Okay, so the two things, and maybe I should talk about this very quickly. Okay, let's do this. So I'm going to consider, forget the presence of all the other terms, I have 5 more minutes, forget the presence of all the other terms. The terms that are of importance to me are the terms that contain the insulation radius. Ri here, the Ri is also present here. Okay, so let me just say approximately, Q is delta T by all of the other things, and then ln of Ri by R naught 2 pi L Ki plus 2 pi R naught L H naught Ri, sorry. Alright, so this is term 1, term 2. Okay, so this entire thing is term 1. This entire thing is term 2. Now you see, here is their individual behavior as I increase the radius. This is Ri. If I plot term 1, which is logarithm of Ri by R naught 2 pi L Ki, the inverse of this particular fellow, I get a plot that looks like this. Sorry, the other way. This is the opposite of the logarithmic profile. So it does something like that. This is term 1. If I look at term 2, which is 1 by 2 pi Ri L H naught, and the inverse of this, okay, so I'm essentially looking at the inverse of the term. If I plot it, its behavior is going to be this way. This is 2. So you see, at a particular value, these two terms, and I should point out this is not the inverse, this is just those particular terms, I'm sorry. Just those particular terms, if you look at their behavior, you see that at a particular radius value, if I add these two profiles up, their effective behavior is something like that. So you see they reach a lowest point at some radius value, which means that at that particular radius value, my heat transfer rate is the highest. This is the combined behavior of those two dominant terms in this equation here. Yes, sir.
So when we have a certain radius, we can think of the insulation is going to be pulling more heat than just ambient air, as far as like thinking about kind of conceptually why it goes up in heat.
Right. But it depends. There are two things that are at loggerheads with each other. If one is low, the other is high. If one is high, the other is low. It's a combined behavior that you need to look at. So that combined behavior is this line here, which is the sum of these two. And that reaches a bottom value at some particular critical radius, which we will call as RIC. And so until I reach that particular radius of RIC, I will see that my heat loss keeps on increasing, reaches a maximum at that critical radius, and then starts dropping down. But it's not sufficient that I just go past this critical radius. I have to make sure that the radius that I choose gives me a heat loss rate that is much more than what I require without insulation. So there are those considerations to keep in mind as well. And this is nothing but a problem of maximizing or minimizing something. And what do you do when you need to maximize or minimize something? You take the derivative of this term with respect to the radius r suffix I, set it equal to 0, you will get your critical radius value. And this is what we will do on Monday. We'll complete this problem. I'll look at one more problem of this nature, and then that will be the end of the preparation for your midterm exam. Okay? Thank you.